In graph 10.1, we showed how marginal willingness to pay curves, just like substitution effects, arise from single indifference curves. We'll now show more clearly the connection between the marginal willingness to pay curve and the substitution effect. We again start out by assuming an initial price P for a gallon of gasoline and illustrate our initial budget constraint. As in the previous graph, we begin with your optimal bundle A that occurs at a gasoline consumption of QA gallons of gasoline, where the indifference curve is tangent to the budget constraint. Now, instead of focusing on the single indifference curve that passes through bundle A, as we did in graph 10.1, let's pretend we're just deriving this consumer's demand curve. Suppose, for instance, that the price of gasoline goes up to P prime. It might then be that your new optimal response is now to optimize at bundle C, dramatically restricting your consumption of gasoline from QA to QC. To isolate the substitution effect, we do what we've always done. We take the final budget constraint and shift it up parallel until it's tangent to the original indifference curve. This gives us our compensated budget that has the same slope as the final budget, but is tangent to the original indifference curve. The tangency occurs at bundle B, where you consume QB of gasoline. Notice that bundle B is to the northeast of bundle C. That is to say, it contains both more of other goods as well as more gasoline, implying that all goods in this case are normal goods. The movement from A to B is then our usual substitution effect. In other words, the substitution effect is the movement that occurs entirely along the original indifference curve that passes through bundle A. On the lower graph, we'll first derive your own price-demand curve as we did in Chapter 9. Since gallons of gasoline appears on the horizontal axis in both graphs, we can simply drop point A down at the same quantity QA and let it settle in the lower graph at the price P, which is in fact the price that occurs along the blue budget constraint where your original optimal bundle A occurs. We can then do the same for bundle C. Bundle C occurs on the steeper magenta budget that arises from the higher price P prime. Thus, as we drop down bundle C at the quantity QC, we let it settle at P prime. This gives us 2 points on our own price-demand curve. In Chapter 9, we then connected C and A to estimate our own price-demand curve, but we also brought point B down from the upper graph. B happens on the steeper slope of the compensated budget, and thus at the higher price P prime, so as we drop it down, it settles at the same height as point C. We found no use for point B other than to indicate where the substitution effect ended and where the income effect took us from there when we derived the own price-demand curve. We'll now see its usefulness. In particular, instead of connecting C and A as we did when we derived own price-demand curves, we're now connecting B and A. The question then is, what does this new curve tell us? Well, it tells us how much your consumption of gasoline will change if we compensate you to keep you just as well off as you were originally. Thus, this curve is sometimes called the compensated demand curve. It tells us how the quantity demanded changes with prices, assuming that the consumer is always compensated to end up on the same indifference curve. Since the consumer always ends up on the same indifference curve along the compensated demand curve, this implies that the compensated demand curve is derived entirely from a single indifference curve, just as the marginal willingness to pay curve was in graph 10.1. The compensated demand curve is in fact the marginal willingness to pay curve that we derived in graph 10.1. You can see this most easily by just looking to see how we translated bundles A and B from the top graph to the lower graph here and in graph 10.1. In both cases, we're modeling gallons of gasoline on the horizontal axis, and so we simply drop the 2 points down to the lower graph. and in both cases we place the points at the vertical height that's equal to the slope of the indifference curve at those points. The marginal willingness to pay curve is therefore generally not the same as the own price demand curve. The own price demand curve is derived by connecting C and A in our lower graph. The marginal willingness to pay curve is derived by connecting B and A. Unless point C is the same as point B, the marginal willingness to pay curve will be different from the own price demand curve. And the only time C and B are the same point in the lower graph is if the underlying good, gasoline in our case, is quasi-linear. In other words, if there are no income effects. The marginal willingness to pay curve therefore incorporates only the substitution effect, whereas the own price demand curve incorporates both the income and the substitution effect.